Students, now in this session we shall discuss the topic functions that are continuous on metric spaces. The previous topic we discussed reformulation, where we studied the new definition of the previously studied definitions, the new format we studied, that is the formulation of new definitions. Before that we studied what are the functions continuous on real line. Now we are going to extend the continuous functions on metric spaces, so where the real line is a special case. So now, the topic we are going to discuss is functions continuous on metric spaces. This is a topic and we shall begin with the definition. So let M comma rho be a metric space. So we take a metric space Vm with a metric rho be a metric space. If A is an element of M, and if I say we take R a real number greater than 0, then we define the set B of A semicolon R is defined to be the set of all points in the metric space M whose distance to A is less than R. That is, I say that B of A semicolon R. This is called as an open ball with center at A and radius R. It's nothing but a set. It is a set of all elements of M such that the distance between the element X and the center should be always less than R. Here we say that B of A semicolon R is called an open ball. It's called as an open ball of radius R about the center A. So about the same center we can construct infinite number of open balls such that the radius varies. So this is the main definition of an open ball in a general metric space, where the metric is given by rho of, that is the distance between any two elements is given by rho of X comma A. Now, the special case what we discussed in the previous topics, that is in real line, this open ball, suppose in one dimensional space, that is a real line. What is an open ball? An open ball is nothing but an open interval, that is of the type A minus R comma A plus R. That is, this is the entire real line. Suppose this is an element A, this is center, and this is removed, that is this is A minus A plus R, and this is A minus. Except these two elements, including the center, all the points in this interval is denoted by like this, and we denote it by this symbol. It is called open ball, whose center is this, radius is what? This is the radius. This is r, and this is also r. So in 2 dimensions, it is r square. This is in r. In r square, what is open ball? You have to imagine that is a set of all elements, ordered pairs, because in 2 dimension we have an element is an ordered pair. Set of all elements x comma y such that x square plus y square is less than r. It's a disk. It is something like this. Suppose a 2 dimension, say, suppose this is a center, I say the boundary is not considered, that's why we put a dotted line. So all points inside this circle, whose center is a and radius is r, all the points inside the circle except we should not consider the boundary, and we call this one geometrically as a circular disk. Circular disk, and all points inside the circle, that is denoted by this formula. If any point following satisfying this condition will be inside this set, and that set we call it as an open ball, whose center is a and radius is r. Similarly, in 3 dimensions, that is r cube, this is r square, this is the example r square. Next r cube, the same symbol, but we are in 3 dimensions, that is x, y and z, such that x square plus y square plus z square is less than r, and this is the inside of a sphere. If you draw a sphere, this is the 3 dimensions. Suppose x is one real axis, y is another real axis, and z is another real axis. They meet each other mutually perpendicular, and suppose there exists a sphere whose center may be this a and radius is r, and all points inside this sphere will come inside this set. We call that as the open ball with center a and radius r, and like this we can extend for n dimensions, and these are all numbers we are denoting with. Sometimes in a metric space we deal with many different kinds of elements. Okay, now so however in an arbitrary metric space there is no such thing as an interval, but the object B of A colon R does have a counterpart in many metric spaces, which is the reason we have it in terms of distance. So you can understand this is the meaning of open ball up to 3 dimensions. In general metric space, we denote the distance function by the rho, and this is the definition of an open ball in any general metric space. There should be radius, there should be a element which is the center of that set. Now, for example, now suppose M is a closed interval. Suppose another one example. M is a closed interval. M is a closed interval 0, 1 with absolute value metric. With absolute value metric. Then the ball, open ball, we have 1 by 4, the center is 1 by 4 and radius is 1 by 2. See, this is a space under consideration, not real line. Only M is a closed interval. This is our space under consideration, and this is the open ball. We say then B in is the interval 0, 3 by 4. So what happens is we draw the entire real line and we take this set, that is 0, 1. Suppose it is like this. All points inside this one and even the endpoints. This interval is this is our metric space. And distance is measured by the usual absolute value metric. That is, suppose any two elements x and y, the distance is measured by x minus y. This is called absolute value metric. The usual way of finding the distance between any two points in real line. So same like this. This is our space under consideration. We are considered this as a space, metric space. Now what is this open ball? Whose center is 1 by 4 and radius is 1 by 2. That is, center is 1 by 4 means, suppose this is 1 by 2, suppose 1 by 4 is here. This is the point, I say 1 by 4. And radius is 1 by 2. So from 1 by 4, what are the elements that is at a distance of 1 by 2 less than 1 by 2? Suppose you add 1 by 4 plus 1 by 2, so this is 3 by 4. So all elements other than 3 by 4 but less than 3 by 4 till this. And what about the right hand side? This 1 by 4 you subtract minus 1 by 2, so he will go here. But our space is up to 0 only. So what is this open ball is? All elements from here to here. I will highlight, I will use a different. See, from here to here, then up to this. But this part is not there in our metric space itself. So how can I write this open ball? How can I write this open ball is? This is nothing but 0 is included. 0 is included along with 3 by 4 excluded. Okay, this is the open ball we learned from this by constructing the real line and seeing it. So not always open interval, like this half open interval also we come across. We have to see the metric space under consideration. So this is one example, and another example is, suppose our metric space is the discrete metric space, the real line only, the entire real line, but any two points, distinct points, the distance is what? 1. If they are equal, then distance is 0. So any two points, any distinct points, the distance is 1. Like this is how we define the metric and on the real line, and that metric space we call it as discrete metric space. Generally real line we simply denote it by R. If I put the suffix D, it is understood that we measure like this distance. The metric is given by D. It is called discrete metric space. And we consider now discrete metric space. Suppose this is the discrete metric space. This is also real numbers only. Only thing is the distance function is varied. We measure the distance between any two points in a different way. Now, what is this open ball? You take any general element, we take any general element, and if the radius is 1, so in discrete metric space this is only one element is present, because So what is this set? Such that set of all elements whose distance between the center A and the other element is less than 1. There is no element, because in discrete metric space any 2 points the distance is 1. So what are the, suppose I take one element A here in a discrete metric space and I take the radius is 1 unit. So how many elements are inside this set? No elements, because less than 1. The radius is less than 1. So suppose B is another element, the distance between A and B must be 1. But here the question is the distance between A and B must be less than 1. So there exists no element in this open ball whose center is A, radius is 1. So this is only for discrete metric space. It's only for discrete metric space. On the other hand, if suppose I increase the radius, that is just 1 greater than 1, any number I take, suppose I take 2 or 1.5, this set will contain the entire discrete metric space, because distance between any 2 points is always 1 in a discrete metric space. If I increase the radius more than 1, then what will happen is all the elements whichever satisfies this property is nothing but the entire real line with the discrete metric value, discrete metric. So these are all important results. Now we are going to define a continuous function on a metric space. Before that, now previously we discussed a function f which is continuous from real line to real line. Now we are going to change this to more a general space. M1, this is another space comma M2. Space means there should be a metric. This set we measure the distance between any 2 elements by the metric M1, rho 1. And in this set we distances between any 2 elements is measured by the function rho 2. So M1 is a metric space, M2 is another metric space. Now we are going to define what is a continuous function on metric spaces. So before that, we'll just give some preliminaries. Let M1 and rho 1 and M2 and rho 2 be metric spaces. Let A belongs to M1 and let f be any function, whose range is contained in the metric space M2 and whose domain contains some open ball, say B, whose center is A and radius is h, with h is greater than. These are all the things we have to keep in mind before defining what is a continuous function on metric space M1 to metric space M2. There must be at least one open ball in the domain. See, like this. This is M1, rho 1, and the codomain is M2, rho 2. And our f is a function from M1 to M2, and this is what, and the range of this function is inside M2, and there exists at least one open ball inside M1. This and all the assumptions. Now we go for the definition. The function, say f, is continuous at a point A in M1 if the limit x approaches a, f of x equals to f of a, where the limit of a function is given by some formal definition already discussed. Okay, so this is the way to express the notation when a function is continuous at a point a. If suppose a function is continuous at a general point, we take it, and if we say that the limit of the function when x approaches a, f of x approaches f of a, then I say that the function is continuous at the particular point. If a is any general point, then I can say that the function f is continuous at every point of the domain M1. Then simply we say that f is continuous on M1. Okay, so these are the things. The next statement, the function f is continuous at a point a in M1 if and only if any one and hence all of the following conditions hold. That is, if any one of these following conditions holds true, then the others also true. That is the meaning of hence all. Suppose the first one is, given epsilon greater than 0, there exists a given epsilon greater than 0, there exists a delta greater than 0 such that is there are two metric spaces. Whenever the distance between f of x and f of a is less than epsilon, this is less than epsilon, whenever the distance between x and a is less than delta. See, this is a metric space M1, this is the metric space M2, whose distance function is rho 2, this distance function is rho 1. So this is what is the definition for a continuous function in terms of metric space. B, the inverse image under f of any open ball B or center f of a radius epsilon about f of a contains an open ball, say B of a colon delta about a. That is, if I take two metric spaces M1 and this is M2, I say that this function f from M1 to M2 is continuous. Suppose this is a, continuous at the point A. If A is here, definitely f of a will be mapped somewhere here. And what it says is, any open ball whose center is f of a and radius is what? Any open ball whose center is f of a, radius is epsilon, this inverse image, the inverse image will fall in M1. Inverse image will fall in M1. So what it says is, if f is continuous, then the inverse image of any open ball about f of a will contain, this is an open ball, say center is A and radius is delta. This inverse image is somewhere falling here. This inverse image something like this. This is nothing but the inverse image of the open ball f of A semicolon epsilon. This is the f of A colon, this is an open ball. The inverse image of this open ball will contain what? This open ball, whose center is what? A, radius is delta. So if this happens for any point A in M1, then we say that the function f is continuous. See, these are the three different like definitions for a continuous functions. If any one is satisfied, then if any one is true, the other one is also true among A, B, C. So now another one, the statement C is, this statement we have proved it for real valued function in the previous sections. Whenever I take a sequence, whenever xn is a sequence of points in M1 converging to A, then the sequence f of xn, in the sequence f of xn of points in M2 converges to f of A. That is, this is already proved in real line. This proof is same as the proof of real valued function. So simply you have to replace the absolute value by the corresponding metric symbol. Suppose A is here. Suppose there exists a sequence in M1, say x1, x2, x3 is sequence approaching A. Then what happens is, so if f is continuous, then there exists a sequence, the corresponding x1 is here, f of x1 is here, x2 is here, the corresponding f of x2 is somewhere here. This sequence f of x2 will come very close to what? F of A. If this is happening for this point A, then we can say that the sequence, the function is continuous at A, because if C is true, then see, these are all the equivalent statements for continuous functions. If any one of these is satisfied, then I can say that the function is continuous. This statement C is already proved in the previous section for real valued functions. Now, what we have to do is, I will show you what are the changes we shall make Yes, this is the theorem. It was proved in real valued functions. A real valued function f is continuous at A. See, this statement C, the proof of statement C, I am giving the hints. I am giving the hints for the proof of statement C. Statement C is generally a metric space M1 to M2. Now already we proved the same result for real valued functions. If it's a real valued function, A is a real valued and the domain M1 and codomain both are M1 and M2. Both are real line in this Okay, so f is a function from m1 to m2, and here what happens if xn is a sequence of points converging to a real number, everything real number a, xn is a sequence converging to a, then there exists a corresponding sequence f of xn converging to f of a. Okay, so there exists a sequence f of xn, that is if xn converging to a, f of xn sequence converges to f of a. We have proved it here. So what are the changes we have to make it for general metric spaces is, here wherever real line we don't use real number. Let be a sequence of, instead of this we have to use the word sequence of points converging to a. So that is very carefully you have to make a note from this theorem 7.2d, and everything is okay. It's given in terms of open board. Okay, so everything is same. Yes, so not need to make any change in the necessary part. In the sufficient part, here, yes, in place of this is from the metric space M1, this one. So what I have to do is, rho 1 of xn comma a is less than 1 by n. This is what you have to make a change, and this is the operations in the range. So M2. So you have to put rho 2 of f of xn comma f of a. This is what you have to make the changes. Okay, in the proof what I have given, this is the reference book. So these are the changes you have to make in that particular theorem, what we proved it for real valued functions. So now we complete the proof of C. The proof of C is completed. So these are the changes you have to make, and you have to write the proof of this. Okay, write the proof of this statement. Now the next theorem is, actually this one you can name it as a theorem. This is a theorem. For this theorem, we have to prove the third one. That one alone you need to prove it. Okay. So now the next theorem is also already proved in real valued functions. Let m1 comma rho 1, there are three metric spaces I am considering, m2 comma rho 2 and m3 comma rho 3 be metric spaces, and let f is a function from m1 to m2 and g is a function from m2 to m3. M3. If f is continuous, if f is continuous at a in m1 and g is continuous at f of a in n2, then G composition f is continuous at a. So the proof is same as what we proved for real line, the real valued functions. Now here, instead of three real lines, we consider three metric spaces, that's all. With three different metrics. This is m1 comma rho 1, this is m2 comma rho 2, and this is m3 comma rho 3. And for sake of simplicity, what we say that f is a function from m1 to m2 G is a function from M2 to M3. Now the range of F, we assume that the domains of F and G are all of M1 and M2 respectively. Okay. So the domain of G is full M2, and that is what we assume here. Now, so what is this is, suppose this is a point A in M1 and G is continuous at, suppose A is M1, this is f of A, and from here it is mapped to G of f of A. Okay, so I name this as B, then it becomes what? G of B. All the points in M1 I named as X, general point. All the general point in this set I named as Y. So to avoid confusion, you can refer that theorem where we used f is a real valued function. So same concept we shall use it, and we have to be very careful which metric we have to use at which place. So now we go to that theorem now. Already we proved it. See here in the first section, the beginning of the section, we proved this one already before the chapter reformulation. Yes, here. This is f and g are real valued function. That is only thing is difference. And f is continuous at A, and g is continuous at f of A, and then g composition f is continuous at A. Same thing. So here this is set A, we say that is also real line, and then this is also a real line B, and M3 this is also real line. You think this is M1, and this is a space M2, and third one is M3. Okay, now everything is same. Same thing is this. We must show like everything is same. Here, see, you can guess what is the space here considered. See, we use the function g of f of x. So this is a function from it's moving. This is a function f. G is a function from this set to this set. Okay. Here in this space the metric is given by row 3. Here the metric is defined by row 2. Here the metric is defined by row 1. For this problem, for this theorem, general metric space. Okay. So now how to change them according from this? See, g of f of x. G of f of x means from here to here. It falls in the third set. So instead of this absolute sign here, what we have to do is row 3 of, that is the row 3 of g of f of x comma g of f of a. That's all. Everything is same. Here x and a, the relationship between x and a is somewhere here. So in place of this absolute things, you have to write it as 0 less than row 1 of x comma a is less than delta. These are the changes you have to make. Okay, and here also this is row 3 of g of y comma g of b is less than epsilon. This is in the second set. Yn I already told you. Here all the elements is of the form y. Here all the elements of the form x. So this is row 2 of y comma b is less than eta. So now what you have to do is everything is okay. Then here also this is in terms of row 2 you have to write. This in terms of row 1 you have to write. Same like this. This also row 2. This also row 1. These are the changes you have to make. Here this is rho 1 in terms of rho 1, this is in terms of rho 3, and this is in terms of rho 1. That's all. So if you change these things, then we have written the proof for the general metric space. This completes the proof. Okay. And similarly, we have the other two theorems. Let M be a metric space, and let F and G be real valued functions, which are continuous, at A in M. Then F plus G, F minus G, Fg are also continuous at A. Furthermore, if G of A is non-zero, then F by G is continuous at A. So the proof of this is already discussed in real valued functions. Functions continuous on real line, already discussed. The same thing, instead of absolute value, you have to use the particular the distance function. Okay, there we used both our real lines, M1 as well as M2. Here we have to be think and write which is M1 and which is rho 1 and what is rho 2. Everything you have to check it properly and frame the theorem. The same thing we discussed in real valued functions. Same like the previous theorem we discussed, you have to change the absolute sign, absolute value metric to the general metric. Now the next definition. So now suppose at one point a function is continuous, we say that the function f is continuous at that point A. If a function is continuous like this at each and every point of the domain of the function, then we simply say that the function is continuous on M1. That's all. So that is a let M1 and M2 be metric spaces, and let f is a function from M1 to M2. We say that f is continuous function. F is a continuous function from M1 into M2 if f is continuous at each point in M1. That is the thing. That is the definition. If each point of that space f is continuous, then we simply say that f is continuous at each point in M, or simply we say that f is continuous on M1. That's all. So now this theorem here, one more theorem we can write, that is the next theorem. Anything they can ask in the examinations. Accordingly, you have to write the proof. So what is the change is continuous at a point A. Instead of this, we have to write the new theorem is f and g by real valued functions these functions for metric space M1 to the metric space M2. So here we have used the word real valued functions. So now if this theorem is if f and g are continuous functions. Fng are continuous functions from a metric space M1 into the metric space M2, then so R f plus g, f minus g, and fg. So okay. Sorry, it's going down. Now, sorry for the break. Here, and fg. If f and g are continuous functions, now it's not real valued, just continuous functions on metric space M1 into metric space M2. So, in this proof, so wherever we have used absolute value, we have to use the corresponding distance function. That's all. So, and furthermore, I think that I forgot. Furthermore, if g of x is non-zero for every x in M1, should be non-zero for every x in M1, then f by g is also continuous on M1. So this is same as the previous theorem, so that is okay. Now, so what is this? One result is there that we can write it like a theorem. Prove that every polynomial function is continuous on the entire real line. The meaning is at every point of R, the polynomial function is continuous. How to prove this? Any polynomial function f is defined as, so how is a polynomial function defined? F is a function from R to R. It's defined by f of x equals to a0 x power of n plus a1 x power of n minus 1 plus a2 x power of n minus 2 plus so on till an. This is how a polynomial function is defined. Now, see the right hand side, this function is defined is like this. We know that any constant function is continuous. Any constant function, that is f of x equal to c, any constant function is definitely continuous. Any constant function is continuous, and the function, identity function, and the function of the form g of x equal to x is continuous. This implies that a constant function is continuous and g of x is also continuous. This implies that c into g of x is also continuous. This is by the previous theorem. If f and g are continuous, f into g is also continuous. That theorem we can cite it. We can cite or we can refer that theorem. So c into g of x is nothing but c into x is also continuous. Now what happens is, if x is continuous, now g of x equal to x is continuous, and hence this implies that g of x into g of x, that is nothing but x square, is also continuous. This is again by the same theorem, you can cite it here. So what happens is, now therefore this f of x, which is nothing but a naught x power of n plus a1 x power of n minus 1 plus a2 x power n minus 2, so on till en. This is what happens is, this is a continuous function, this is a continuous function, everything is continuous function. By the previous theorem, sum of two continuous function is also continuous, and this is continuous, and sum of this one and this one is also continuous. So overall is a continuous function. The same theorem we can cite it previously. So hence every polynomial functions are continuous on the real line. You can write your own proof. They ask, you can write your own proof. We know that constant functions are continuous there, and identity function is continuous. Therefore, constant function into identity function is continuous. That is one result you can keep in mind. Then this polynomial a naught into x power of n is nothing but sum and product of continuous functions, and hence by the previous theorem the resulting function is also continuous. Like this simply we can write it. Don't want to explain like this also. So this completes the proof of this theorem, and the final part of this section is final part. Prove that every function defined on RD, every function from RD into any other metric space, into a metric space, is continuous on RD. So you have to prove that any function you take that is continuous on the entire RD, that is, we are going to take one general element of RD and prove that a function is continuous, then it is automatically continuous for every element of RD. Therefore, we can say that any function defined on RD is continuous. So how to prove this one is, you take any element A in RD, the open ball, already we discussed this one, the open ball B of A colon 1 is nothing but only one element, contains only the center, contains only the point A. Thus, what happens is, for any epsilon greater than 0, see, we are going to use that definition of a continued function, that equivalent statement we are going to use it. For any epsilon greater than 0, the inverse image under F of the open ball B of f of A colon epsilon contains certainly contains the ball is the open ball B of A colon 1, because inverse image of any this open ball will contain minimum this point A. So this is nothing but the point A. So definitely this inverse image of this open ball will contain this open ball. This is sure. So this implies that, by the three equivalent statement, this implies that F is continuous on at a single point A in the discrete metric space RD. Since A is arbitrary, we can say that F is continuous on every point of RD. Simply I can write it, F is continuous on RD. And F itself is a general function. Therefore, any function, and we have taken F is any other function. And the function F on RD is not required. It is a function on RD only. It is understood. So what happens is, any function on RD is continuous. This completes the proof. So this completes the section continuous functions on metric spaces. You have to write a lot of things is there. You have to define properly, state the theorems. I have given a lot of hints. So complete the theorems, and we will see in the next session, that is open sets, closed sets as another section, and finally discontinuous functions on R. Thank you.